Okay, welcome to part 5.11. All right, here's where we are. Okay, we started off. Okay, so remember we're going to create a likelihood function to describe how to estimate nominate scores. And basically, the recipe function I gave you, you'd say, what's your dependent variable? And it's going to be how everyone votes. So it's like how legislator one votes on roll call one, a legislator two votes on roll call one, a legislator three votes on roll call one, and then how legislator one votes on roll call two, so on. You got lots and lots of cases you've got to explain. So if we take any one of those and we'll say, let's look at say roll call one, and we can say that the yay alternative was the bill, and we'd say what we want to know, what's the probability that legislator I will vote yay or for the bill. So it's going to be looks like this. Okay, remember it's partly because that error term is logistic. It's going to look like this, except we've got to substitute the UIB and UIQ. Okay, and that was on the next board. So we said if the bill is the yay alternative, Q is the nay alternative, we define their locations as, and this is roll call J, okay, as ZJY, ZJN. Then we define the distance of those bill locations from person I's ideal point, that's DI, JY, and DIJN. Okay, the utility is E to that. Okay, so let's put them together now. Okay. Okay. Let's see. On roll call J, probability I votes yay. Okay. So this is going to be E. Let's do this. It's E to the UIB minus UIQ. Okay. E to the UIB. Now, UIB is this term. Okay. So it's E to the stuff. E to the E to the negative D I J Y squared. Okay. That's E minus utility of Q, which is the nay alternative, minus E to the negative D I J N squared. Okay. All divided by one plus E to that same term. 1 plus E to that same term. Okay. It's going to be 1 plus E to the E negative D I J Y squared minus E to the negative D I J N squared. Okay. Now, that's the simplest form. Okay, but here is where Poole and Rosenthal add some bells and whistles to that. They say, well, okay, this is basically what you get when it's standard logistic. What if it's not standard logistic? The error term, the variance of that logistic error term is not 1, it's something else. If so, the way you can handle that is you can put in a beta here. So that's what they do. For the utility, they just multiply beta times the utility. Okay. All right. Now, the other thing they do, okay, is they add in another constant. Okay. And this is, they put in omega squared here. Okay. Here is why I think they do that. Okay. When you talk about the distance, okay, you have these ideal points on a line. They want to normalize everything so that the ideal points are between -1 and 1. Okay. It's like that Spinal Tap video. You say, on Nominate scale, how much more liberal is Teddy Kennedy than Strom Thurmond? He says, well, he's 2 more liberal. Okay, well, where'd you get that scale? How did you define units? It's like Celsius. How you define units by taking water, the freezing point and boiling points of water. Take however the distance between those two temperatures, divide by 100. That's a unit. Okay, they're going to do something similar with that omega squared. They want to fix units. And now, if you notice these DIs, suppose you blew up your scale. So whatever scores you had, you multiply everything by 10. Okay. That shouldn't affect anything. And so that's when they put in this omega squared. So this omega squared is a constant that they estimate. And if you blew up everything by all the distances by 10, and at the same time made all these omega squared, shrunk them by 1/10, you would not change these probability terms. And so basically what those omega squareds are doing is setting the scale. Like it's like basically deciding whether your units are centimeters or meters. And so by picking the right omega squared, they can make sure that all these distances are between -1 and 1, or in other words, also making sure that the actual scores are between -1 and 1. So that's what's going on with that omega squared. Okay, don't get too hung up on that. As you'll see, by putting in that omega squared, it causes an identification problem, because that you've got to set omega squared to something. And what Poole and Rosenthal do is they pick an omega squared just right so that all of the scores will be between -1 and 1. If they'd picked a different omega squared, they could have made all the scores between -10 and 10, or the even different omega squared, they could make it between -100 and 100. Okay, so that's what the omega squared is doing. Okay, the beta is a little bit trickier. It's just the fact of how much weight to give on the scene utility versus that error term. That's kind of what's going on with that beta. Okay, now let me give you the answer to. Okay, no. So let me write now. Okay. Okay. So next. Okay. Let me show you what the likelihood function is going to look like now. Okay. All right. Now, okay. Let's see. One more thing before I do this. Let me show you how you can rewrite this. Okay. Note that if we multiply numerator and denominator by e, let's see, by, e to the beta e negative omega squared dij n squared. Okay, so we're multiplying it e to the this term. Okay, multiply numerator denominator by that. What that is going to do, we have e to this plus this, e times another number. The rule is you subtract exponents. So we're going to subtract, you add exponents. So that's going to cancel with that. So what that's going to do is it's going to get rid of these two terms here, but we're going to multiply that times the 1. And so that term's going to appear here. So once we do that, we can say probability I votes yay equals e to the, here, I'll do it farther down. E to the beta e negative omega squared d I j y squared divided by this term times 1, e to the beta e negative omega squared d I j n squared plus this term, e to the beta e negative omega squared d I j y squared. Okay. That's what it's going to look like. Okay, this is getting complicated. I realize that. Okay. Let me now write the likelihood function. Okay. Okay. L. Okay. L is going to have a lot of stuff in it. It's going to have all the ideal points, all the xi's. It's going to have all the zj's. There's a lot of parameters to estimate. It's going to have that beta. It's going to have that omega squared. It's going to equal the product over I, over all the people, the product over all the j, all the roll calls, and then we're going to just put in here the probability that the legislator votes yay or nay. Okay. Now, let me go back to this term. Let me first just write the denominator. Okay. So it turns out, so this is the probability that the legislator votes yay. The probability that he's going to vote nay is 1 minus this, and it turns out it's exactly the same, except you just replace the y here with an n. Okay. So either term is going to have the same denominator. Okay. So here's what I'm going to do. The probability that the person votes yay or nay is going to have the same denominator, and it's 1 to the e to the, let me copy this, e to the beta e to the negative omega squared d I j n squared plus e to the beta e to the negative omega squared d I j y squared. Okay, now that's times. Now, let's assume that it's a case where it's a yay vote. So then in that case, the numerator is just going to be e to the beta e negative omega squared d I j y squared. Okay, but here's what I'm going to do. I'm going to do a trick. I'm just going to say multiply this times an indicator variable I votes y on j. So that equals 1 if person I votes y on j. It equals 0 otherwise. So multiply. This is the denominator times the numerator. And so this is plus a similar term, e to the beta, e negative omega squared d I j n squared times an indicator I votes nay on j. Could have just made it 1 minus that indicator, but anyway, it's a little more, maybe it's a little more transparent this way. Okay, that's the likelihood function, okay? All right, there's a lot in it. And all these d terms, there's a zy or zn, and there's also an xi, right? Okay, there's a lot going on in here. Okay, I'm going to flash that likelihood up in a second. All right, now, I gave you a homework problem, and I said, be ready to discuss this in class. Okay, and here was the homework problem. Okay. Actually, I don't have it in front of me. I might be looking at an old version. If I am, and it doesn't quite match your homework problem, you should be able to get it. The same principle. It won't matter if I'm giving you the exact numbers or not. So what I asked in the homework problem is I said, suppose that here were you maximize that likelihood function, and you got for person one, so legislator one, you got his or her ideal point is 0.1 on the first dimension. By the way, so far I've said dimensional on one dimension, but once we're talking about distances, you can create the same distance if you have points in a two-dimensional space rather than a one-dimensional space. We all understand distance, okay? So the key is you just take those distances, the distance of an ideal point from a bill location, square it, that distance, square it, and just plug it into the likelihood function. So it shouldn't be that much harder for you to imagine this in two dimensions. Okay, so that's what I'm going to do. I'm going to say the ideal point of legislator 1 is 0.1 on the first dimension, negative 0.2 on the second, x2 equals 0.3 on the first dimension and 0.4 on the second. And then the bill locations, we had z1, y, so roll call vote y. Roll call 1, the yay alternative is 0, 0. Z1 nay equals 0.1, 0.1. And then I gave you the bill locations for the yay and alternatives on the second roll call vote, and then the yay and nay locations on the third roll call vote. So this would have been 4 more terms. I'm not going to write them here, okay? But here is what I'm going to do now, okay? Let me just graph all these on a two-dimensional space. Okay, so this is dimension 1. This is dimension 2 on the Nominate scale. On person 1 was at a 0.1 and negative 0.2. So this is x sub 1. Okay. X sub 2 was 0.3 and 0.4. So x sub 2 is here. Okay. I'll write in black the ideal points. I'm going to write in red the bill locations. Okay. ZIY is here, the 0, 0 point. ZYN is at the 0.11 mark. Okay. So let's say that was bill location on the first roll call. Let's use a green. So I'm not even going to use I'm going to look at the homework. I'm just going to pick 2 arbitrary points. So, by the way, this was red is roll call 1. Here's the yay alternative. Here's the nay alternative. We'll call it Z. Z1 and Z1Y. Okay, let's use green for roll call 3. So let's say Z2Y is here, and Z2N is there, and then I'll use orange for Z3Y and Z3N. Okay. I actually don't think these actually correspond to the what I actually wrote on your homework, but it won't matter. Okay. All right. Now, if that was what Nominate reported to you, so you said Nominate, okay, here's the data. Here's all the roll call votes. Give me an estimate of legislator 1, legislator 2, and then the bill locations, yay and nay, for the 3 bills, the 3 roll call votes. So there's going to be 6 alternatives. There's a yay and nay on each of those 3 roll call votes. So there's 6 Z's, 2 ideal points, okay? Okay, plug those into there. I told you, Nominate says, those, here are the X's and the Z's that maximize that likelihood function. Now, the homework problem, I said, tell me another set of X's and another set of Z's that would also maximize the likelihood function, okay? If you want, pause it, try to think of this for a second, okay? Hope you're back. Here's the key, okay? Notice that if we're going to compute the likelihood function given these parameters, okay, remember that the X's, we call them X's, but they're actually estimates. We should have used a Greek letter, I think, to call them. They're not data. These are then Z's also, they're not data. Those are estimates, okay? How do we use these to compute the value of the likelihood function? Well, remember, to compute the likelihood function, we have to compute the distances from all those. So what we would have to do, so for person 1 on roll call 1, we would have to, I'm going to use light green, we'd have to compute that distance, the distance of 1's ideal point from the yay alternative, and then the distance of 1's ideal point to the nay alternative, okay? Once we had that distance, we plug that in to the likelihood function, and we don't even need, once we give it the distance, the likelihood function doesn't need the actual value of the X's and Z's. All it needs is the D's, okay? So that is the key. If we could compute all of the D's, X1 to those 2 roll call votes, X1 to those 2 roll call votes, X1 to those 2 roll call votes, and then do the same for legislator 2, X2 to those 2 roll call votes, X2 to those 2 roll call votes. Compute the distances for all of those. We no longer need the X's and Z's. We just feed the D's, the distances, into that likelihood function. Okay, so that's the key to the answer. I said, can you tell me a new set of X's and a new set of Z's that also maximize the likelihood function, that do just as well, that will keep the likelihood function at the same value? The answer is, if you can tell me a new set of X's and a new set of Z's that keep all these distances the same, that works, okay? How do you do that? Okay, one way is to just shift all the X's and the Z's to the right, or shift them, 1 unit or 3 units. If you shift all of them the same amount, that preserves the distances, and therefore the likelihood function is going to remain the same. Similarly, if you shifted them all up or shifted them all northeast, if you did distance the same amount, it's not going to change the likelihood function. Also, not only that, you can flip this thing. So if you flip it, make it look like the mirror image of it, that also preserves distances. Same thing, you flip it this way, okay? So there's a variety of ways that you can give me new x's and new z's such that it does not change the value of the likelihood function. And so what that means is that likelihood function is not identified, okay? Poole and Rosenthal, they have to do, I call it kludgy aspects. They have to, basically with seed values, by putting in the right seed values, they can get it so that it doesn't wander off into all these crazy values. So, what would keep the computer from saying, oh, here's one set, let's try another set of values 10 units that way. That would work just as well, okay? How do you prevent that? Well, it's basically seed values, and they put in some other kind of bells and whistles to prevent that in their computer program. Okay, so that's the answer to your homework problem. So I've already explained it. Okay, all you got to do is just, I said, be ready to describe it in class. So actually, if you your homework is to understand what I just said. Okay, you don't even have to write anything for that homework problem. Okay, so that is the final segment. Okay, see you next week in session 6.